Okay, hello everyone. Welcome to today's session on optimizing performance for Amazon S3. It's probably one of the last sessions of today at least. So let's make it worth it. My name is Christoph Bartenstein. I'm an engineering director here with AWS. I'm with S3 for about 10 years, and so the last few years I spent quite a bit on performance improvement, thinking about how we can improve performance for customers, for our systems. Now with me is my colleague Valentin Flankert, and he is a principal scientist. And today we'll really talk about how you can optimize performance for S3. We'll talk a little bit about why storage performance matters. We'll give you some examples, show you some custom examples, what they have done with performance, what it impacted to them. And then we'll talk about what the mental model on performance is, the difference between request performance, workload performance, how you want to think about the request, what the request is doing when we go into S3, the architecture behind that a little bit. And then we go really into some of the improvements we have done over the last few months. So we had a bunch of launches over the last few months, from new storage classes to new libraries, new files, etc. And so we'll talk about them, and then we'll talk about how you can actually apply them. So if there's one takeaway for today's session, then it's really about how you can apply all those performance improvements to make your application faster. Well, let's get started why storage performance matters. Well, raise your hand if you store data in Amazon S3. Well, here we go, quite a lot of folks. And you probably at some point run into some challenge with performance. Is it because you're running into throttling, or because the latency was not right, or because just the experience for end customers was not what it was? And some of it is because when you think back about all those different use cases on S3, there are quite a bit of differences, right? So performance requirements for a backup use case versus a data lake use case versus running your machine learning models on S3, it's quite different. So that's one of the reasons why performance matters. The other reason, and customers tell us this more and more, is because when you think about data, it's actually growing faster than ever. And that kind of means two things for customers. On the one hand, it means performance unlocks your data. You get more value out of your data. And it's because you get quicker insights, you can get those insights faster, you can do more with those insights, and ultimately you can have, for example, a faster go-to-market strategy, reacting faster to trends, and so on. Now there's a second reason, which is faster workloads also mean a better customer experience. So think about whatever you have for application where performance matters then for your end customer. If you can serve content faster, for example, it impacts actually end customers. So ultimately, performance, we believe, unlocks your data, and customers tell us this over and over again. Now, the second reason in a world where data is growing faster than ever is that performance really drives cost. And that's an interesting one, because when you think about your bill, storage is probably not the largest line item. So it's probably that compute might be much bigger. And so one of the really important things here is you want to make sure that your compute resources are really utilized. And so you want to make sure that you get your storage out of S3 really quickly, and you want to make sure that when you store it, you get it really quickly back. Because when you get the right performance, you drive up your utilization of your compute workloads, and that means you can drive down those total costs of ownership. Okay, so the big question is when we talk now with customers, well, that's nice, so I understood that. How do we get actually started? Well, let's talk a little bit about how S3 works and the difference between a request and the workload, actually. Now, you said a lot of folks store data on S3. Well, let me give you a little bit of an architectural overview how S3 works. And this is really the 10,000 feet overview. There are many sessions around where you can deep dive. But fundamentally, S3 is a very large distributed service. We store over 400 trillion of objects. There are exabytes of data, hundreds of millions of requests per second. And so what that means is that for every single request, so every single request you are doing when you're writing data into S3 or reading data from S3, what's happening behind the scenes is that the client is doing a DNS lookup. It connects to the web server. The web server then looks into the index. The index is an internal system, and the index just shows the request. Okay, they're the storage fleet. Look over there where your storage blob is. It goes to one of the many storage servers. From the storage server, then all the data is getting streamed back to the client. Now, obviously, there are many more steps there, but fundamentally, you can already see that for a single request, there's quite a bit of work to do. And so if you have a workload, oftentimes you have multiple requests. And so the takeaway here is really that, the requests matter. And the single request is doing a lot of work, and there are a lot of steps to take. And when you think about what's happening behind the scenes here, when you look into a single request, what's happening is the mental model around is you have an overhead, and the overhead is really time to first byte. And so for every single request, you have that overhead. And what that means is that, you want to connect to the server, you want to make a handshake, the authentication, etc. So that is happening for every request, so therefore you have the overhead. And then until data starts streaming, that's the data transfer, that's the second part. And so ultimately what you want to do is you want to make sure that you are reducing that overhead as much as possible. And Valentin later on gives some examples how you can do that. Well, the important part is every request has two parts. There's the overhead and there's actually the data transfer part. Now, that matters because when you think about workloads, and all of you have applications with different workloads, then some of them are latency sensitive. So let me give you an example. Let's say you store a picture on S3, and you want to retrieve that picture because you want to serve that picture to your customer for whatever reason. It's a picture of a dog. Well, in that case, it's really about the latency for that request that matters. And you want to make sure that you optimize that request. Now, it's different when you have another workload where you have, for example, an ETL job. You run like thousands of millions of requests against S3. And remember, S3 is a very large distributed system, which means like you can scale horizontally very, very broad. And having thousands or tens of thousands of requests is quite normal. Now, in those use cases, it actually matters not so much about the single request latency. It matters about like what this entire workload is doing. So it's really throughput sensitive. And for throughput sensitive workloads, the aggregate throughput is what really matters. Now, those two workloads, and we'll come back to them over and over again, quite matter a bit. And Valentin will later talk about some of those implementations and what customers have done. But just as a heads up, what you can do now when you figure out like what your workload is sensitive about, you can parallelize different requests. Again, you can distribute it across S3 very widely. You can reduce the overhead. For example, you can put many objects together. You can sum them up. You can do prefetching. You can caching. And so all those techniques will come back. But that's a little bit the mental model around how to think about performance. Now, one other aspect, and this comes on over and over again, is how do you want to measure requests? How do you want to measure performance? Well, if you can't measure it, you can't really improve it, right? And so every time when we work with customers on performance optimization, it's really important to understand actually what's going on. Now, the good news is in S3, you have multiple services and features that help you with that. So you can see actually performance metrics for your workload with, for example, CloudWatch or with Amazon S3 Storage Lens. And if you want to have those metrics on a very detailed request level, so if you want to know for each single request what the performance looks like, then you can look into Amazon S3 Server Access Logs. And so there are multiple ways what you can do here. And again, the important thing is if you want to measure something, if you want to improve something, you want to measure it. There are different ways how you can measure it. And depending if your workload is latency sensitive, you want to think about first byte latency, last byte latency. If your workload is throughput sensitive, you want to think about aggregate throughput. You actually want to think about the request rate. And we'll talk about that a little bit more. But fundamentally, you have a certain request rate for each prefix. And so you want to make sure that you're not getting throttled. So you want to measure the 503s. OK, so that's a little bit on like the fundamental mental model around like performance. I don't want to go too much into the theory. I want to give you some examples of how we have improved performance and how you can actually use that. So let's talk about some of those improvements we have launched over the last few months. And there were actually quite a bit. So that's just like an overview of some of the highlights. A few months ago, we launched Amazon S3 OneZone Express. It's a new storage class. It's a high-performance storage class. It's providing low single-digit millisecond access. Then we have like a new library called the AWS Common Runtime. I'll talk about that in a second. We launched MountPoint, which is a new file connector. And then, and that's actually really exciting, we launched a few contributions into the open source world with S3A and S3 File.io. I'll talk about some of those contributions and why it really matters for your data lake as well as for your machine learning use cases. Now, before we go into the different improvements we have done, let's step back for a moment. Look at the slide behind me. You see all those different storage classes. And so S3 has launched quite a bit ago, and so we launched different storage classes over time. And what they're doing is they give you a price performance depending on what you need. So you have S3 standard for tens of milliseconds of access. You have SIA if you don't access your data as much. You have intelligent tiering if you don't want to do the work to move data between the left and the right. Intelligent tiering is doing it for you. Then you have those archival storage classes. They really provide you like the lowest cost, sometimes for high retrieval. And then the new one is fully to the left, and that's really S3 Express One Zone. And that provides you single-digit millisecond access. And so I want to talk about that a little bit because it's really exciting, and we see a lot of customers using that. Now, with Amazon S3 Express One Zone, what's happening is you're getting single-digit millisecond latency, you're getting very high throughput, and ultimately, you can improve your performance by 10 times, and at the same time, and that's a really interesting one, you can reduce your request cost by 50%. In comparison to standard. So it's really optimized for frequently accessed data. It scales to millions of requests per minute, and it's really ideal for machine learning training, interactive analytics, content creation, when you talk with media files, and so on. So you get the point. It's a storage class, a high-performance storage class, optimized, where you access frequently over and over again the same objects, and for that, you get like really nice performance improvements. Now, looking a little bit behind the scene, because customers often ask us, okay, how is it done there? It's architected in a certain way. So One Zone Express, as the name maybe suggests already, stores data in a single availability zone. And that's quite different to all these other storage classes who store data in multiple availability zones. And what that means is you can now put your storage in the same availability zone as your compute. And so because you have like this locality, you have it in the same zone, you get like performance improvements for that. Then S3 Express One Zone stores it on a special media, so on a very fast media, in comparison to S3 Standard and SIA. It also has enhanced authentication, enhanced overheads, etc. And that's also new, it has a new bucket type. So it's not a flat bucket, it's a hierarchical bucket, a directory bucket type. And so all those things together give you like these performance improvements I mentioned before. As I mentioned, Amazon S3 Express One Zone is quite popular, so we have a lot of customers who use it. One example is behind me. Lyrebird is a customer, and it's a Lyrebird Studio specifically, and they develop mobile apps. What they have done, they store the data on S3, and so a subset of the data, they move to Amazon S3 Express One Zone. And so for that subset, they know it's frequently accessed, and because it was like frequently accessed, it was on Express, they get faster, much faster retrieval times, and at the same time, they were able to reduce the entire total cost of ownership by about 18%. So quite an interesting example. Okay, well, that was Amazon Express One Zone. The two other points I want to make is it's a storage class we keep on investing, because that's a little bit the theme I want to bring to you, is we invest quite a bit into performance. For Express One Zone, we launched Append. Append just launched last week, and now you can do for the first time appending objects. Before, you had to rewrite an object if you want to change something. Now you can say, okay, not rewriting, just appending, and you obviously get for that quite a bit of performance improvements. We also now have lifecycle exploration, we have KMS support, and so on. So it's really a storage class which is more and more and more popular, and customers, when they talk with me about how they can optimize performance, use it more and more. Now, let's talk about something else. Let's talk about the AWS Common Runtime. So who in the room has heard about the CRT, the Common Runtime? Fantastic, some have heard about it. Who has paid for it? Well, I hope no one, because actually it's for free, so that's the nice thing. And it's doing all those optimizations under the hood. And what the CRT, the Common Runtime, is doing, it's really like a summary of best practices. It is a summary of best practices for IO-intensive workloads. And so it's doing that by, it's written in C++, and it's doing really like optimization of timeouts, optimization of retries, load balancing, parallelization. And it's doing all of that behind the scenes. The CRT launched a few months ago. It's also integrated in many of the SDKs. So for example, if you use the Java SDK, the CRT is now fully integrated into that. And it gives performance improvements of like, for downloads of 2 times. Now, the example I want to give here is how the CRT is working. I mentioned already that the CRT is for free. And the CRT really sits between the client and Amazon S3. And so what's happening is that when you do a request from your client, to the CRT. That request is then optimized. For example, one request gets into parallelization. It's broken down into multiple requests, gets to S3. You get like this optimization on the throughput because you parallelize, and the data gets moved back to the client. You will not see that. All of that is happening behind the scene, but it's a good example how you can really optimize performance for those throughput-sensitive workloads. Let me give you an example how it works. Let's say you use the AWS CLI. You want to download 101 gigabyte files for whatever reason down to your instance. Now, if you do that with the CLI, it takes about 8 minutes. If you do exactly the same thing and you enable the CRT in your SDK, it's doing that 2 times faster in 4 minutes. So point being, you get performance improvements under the hood, especially for I/O-intensive workloads, so throughput where throughput matters. Okay, well, let's talk about another improvement. Sometimes customers have file applications, and they still want to store data in S3. And they want to store data in S3 because maybe they don't need to be POSIX compliant. Maybe it doesn't, they want to scale the way how S3 allows them to scale. And so for those customers, we launched MountPoint. And MountPoint is a file interface, and we introduced it last year. And what it does is you mount it to S3. All the objects are shown as files. When you do an API call on your file application, it translates that into a REST API call. And it provides under the hood, it's integrated with the CRT, it provides under the hood performance improvements by prefetching data, by optimization of sequential data, by caching data. And it's one of those things where customers who have file applications, again, you don't need to be POSIX compliant, but they want to use S3. A lot of them use MountPoint. The interesting thing now for MountPoint, we also launched this week and last week quite a few improvements. For one now, MountPoint is supporting multi-NIC. So if you have EC2 instances with multi-NIC support, you're using multi-NIC to get like really broad bandwidth in, then now MountPoint supports that as well. So you get like much more data out or into S3. The second thing, and we should really talk about that a little bit because it's very exciting, is distributed caching. So I mentioned before you have S3 standard and you have S3 Express, so those 2 storage classes. And what MountPoint is doing is you can have your data in S3 standard, and then you get it out of S3 standard, you can cache the most frequently accessed data in Express. And so in addition to your local cache, you now have a distributed cache. And what a distributed cache means is you don't have to think about how big this cache should be. You don't have to scale it up or down. You can just use it as you want, and you get the performance improvements of Express, but still have your data stored in S3 for durability, availability, etc. And you can also have append as part of MountPoint. Now, just to give you another example, Continental, automotive supplier, many of you know, they have a workload where they store data on S3, they move it out of S3 for data simulation, test simulation. They move it into their Docker containers, and they have used MountPoint to really get this fast out. So the improvements were about like 20%, so quite impressive on that end. Okay, well, machine learning. It's one of those use cases you probably talk a lot about. I'm sure you'll think about what you can do with machine learning. You probably think about how S3 is supporting that. And there are many ways how S3 supports that. We have a lot of customers who have the use cases on S3. Now, when we talk with customers, it's really interesting because they oftentimes tell us, well, one big challenge they have is they want to make sure that the GPUs they're buying, they're using, they're highly utilized. And so what that means is you really want to get your data quickly out of S3, but at the same time, you want to also make sure when you run your machine learning models, and oftentimes your training models over several, sometimes hours, sometimes days, you oftentimes want to checkpoint quite frequently. So you want to write it back into S3, those checkpoints. And so what you want to do is you want to make sure that you get data fast out and checkpoint it fast back in. Now, oftentimes customers use PyTorch. Who in the room uses PyTorch? Okay, actually not that many. Okay, interesting. Okay, so we hear a lot from customers to use PyTorch. It's probably one of the most popular machine learning frameworks out there. And so what's happening is that we launched a connector for PyTorch. So that's fairly new out there. It's an Amazon S3 connector for PyTorch. It's really optimizing those training jobs. And so you get like training data up to 4 times 5 point faster out of S3. And then this week, we launched distributed checkpointing, which means that now you also can checkpoint in a distributed way and get data faster back into S3. So 2 exciting launches we had. If you haven't done so, if you want to play around with it, I would suggest check it out. Again, PyTorch is a very popular framework, and it's now working with S3 very well by just connecting to S3. That's a little bit on the connector for machine learning. Another use case I want to talk about is our data lakes. So S3 is a very popular place for data lakes. There are tens of thousands of data lakes on Amazon S3. And so we thought about how can we help customers to optimize their performance for their data lake. And so when you think about the data lake, the most popular file format, or one of the most popular ones, is Parquet. And so in addition to having the Parquet file format, and there are over exabytes of data of Parquet in S3, you also want to think about how that is connected. And a lot of customers tell us they connect to their data with a connector like S3A or S3 File.io. And so then we thought, okay, how can we optimize performance for those use cases? Well, let's step back here for a moment. What we did then is to say, okay, let's look into a Parquet file. So many of you know that, right? So a Parquet file consists of the footer size, it has a footer, and then it has the actual row groups. So that's a Parquet file. Now what's happening typically is that first there's a request to the footer size to figure out how big the footer is. Then there's a request to the footer, and then there's a third request to figure out where the data sits, and there's a third request to the data row group. So you can already see quite a few requests. So we asked ourselves, okay, how can we optimize that? And the first thing we did is we said, okay, if we can just overread the footer size and just have one request, and we started with playing around with the request size, and that's exactly how we improved the first request. So we went from 2 requests to 1 request by just overreading. We read 1 megabyte, and 99.9% of footer sizes are captured with that. Or say it a different way, 99% of footers are below a megabyte. So that was the first improvement we did. Now, the second improvement is customers told us, well, actually, and we saw it in our data, when you think about the footer, there are requests over and over and over again to the same footer. Well, so we cached that footer, and we get performance improvements out of that. And then the third improvement is we talked before about parallelization, right? And so we asked ourselves, okay, how can we optimize all those different requests to those data row groups? And what we can do is we can use the CRT I mentioned before to go really broad and optimize performance, optimize throughput by parallelizing. Now, all those improvements, we moved them together and we open sourced them. And so here you can see we open sourced them in something we call an analytics accelerator library. It's out there. You can check it out in the GitHub repository. And it's very new. It launched last week. It's an alpha release, so feedback is welcome. But what you see what the thing is doing, it's prefetching sequential access, it's doing this prioritization, it's caching of Parquet file footers, and so on. So it's doing all that work for you. You can just connect to this library and then get the gains out for that. So that's a little bit some of the open source contributions we have done recently. Last but not least, I want to talk about one of the launches. You probably have heard about when you listen to the keynote or listen to Milan in the storage keynote about Amazon S3 tables. And that is a launch that just came out this week. It's a completely new feature. So it just launched this week. It allows you to store tabular data on S3. And what's really interesting, it takes advantage of all those iceberg optimizations like compaction or snapshot management. And the outcome of that is that you get 10 times higher transactions per second. So quite a bit of improvements over S3 standard and 3 times improvements for query performance. Again, it's a completely new feature. It just came out. We're very excited about it. I think you will hear much more from us on this end. And so those are some of the improvements we had. Well, I will pass over to Valentin now, but I want to share with you the improvements you have seen from the storage class to the CRT, to the library, to those open source connectors. All of them, Valentin will show you how you can use them, and you will see much more from us over there. So, Valentin.
Thank you, Christoph. Let me talk a little bit about how you can go even further to improve performance of your workloads. So my name is Valentin Flunkert. I'm a scientist here in S3, and me and my team have worked a lot on analyzing the data, the access patterns, and what we can do to optimize performance. And I want to give some of this sort of knowledge to you. So let's look at the main levers that we have to improve a workload performance. So one of the main factors we can improve is parallelization. By increasing parallelization, we basically improve the performance of our workload. So that's one of the biggest levers, and we'll go into that in more detail in a second. Then looking at a single request, we can reduce the overhead of that request. And then we can also apply prefetching and caching, which speeds up workloads as well. OK, let's talk about the first optimization, which is parallelization. So parallelization is really critical because it improves your overall throughput. And the way you typically do that is by sending many, many requests in parallel. So you can use multi-part uploads to upload data in parallel. And you use many parallel range gets to issue download in parallel. One thing that's very important here is that you have to partition your data well, such that you don't see any throttling with this high parallelization. So let's look at this in a little bit more detail. So a workload is typically not just a single request, right? Your workload may have thousands or millions of requests. And here you see on the left a workload that is sequential. So what happens is your application sends a request, waits for the data to come back, and then sends the next request, waits again, and so on, right? So that is, of course, very inefficient in some sense. So what gives you much better performance is if you can parallelize these requests, right? So you can see how much you can improve the performance here by sending many requests in parallel. And let's look at an example. So if we upload let's say we upload a 100 megabyte file to S3, we can send a single put request to upload the data, and that will give us a certain throughput using a single connection. Now, what actually works much better is if we break the object up or the file up into smaller parts, and then we upload all these parts in parallel using multi-part uploads. So this gives you much, much higher upload performance, right? And here's how this looks like in the CLI. Instead of sending a single put request, you issue this multi-part upload, and then you send many parallel part uploads. And the same is, of course, true when you download data, right? So in this example, we have this 100 megabyte object. If we download this using a single connection, we get roughly 90 megabytes per second throughput. If you parallelize the download, you can get to much higher download rates. And S3 can actually give you hundreds of gigabytes per second for a single object if you parallelize enough, right? So you get really, really high throughput by parallelizing download. So this is one of the main ways you can improve performance in your application. And here again, this is how you do this in the CLI. You can download single parts, or you send range requests to download certain chunks of your data. So one important thing to note here is that for many of our clients, many of the clients that we use, so like CRT and MountPoint, these clients do these optimizations out of the box, right? So you don't have to do anything. If you use CRT or MountPoint, they will parallelize upload and download automatically for you. But if you have your own application logic, then it's really important that you make use of this parallelization and you don't block for a request before you send the next request. OK, so if parallelization is so great, and we can speed up our workloads so much with it, can we basically parallelize more and more and more to get ever higher performance? So unfortunately, that is not the case. There are some limits to parallelization. And the reason is that this parallelization puts load on your client, right? So whenever you send a request, your client uses some CPU, some memory, part of your network, and so on. And the more you parallelize, the more load you put on the client. And what happens is that at some point, when you parallelize more and more and more, you will see that each single request will take longer. And that is because that request, your CPU is busy processing the other requests, right? So each request starts to take longer and longer. And so at some point, you see diminishing returns, and if you parallelize even more, you will actually slow down your workload. So I want to be clear that we, more often than not, we see that customers use too little parallelization, right? So this is like going to the extreme case. If you use really, really high parallelizations, then you see this slowdown. But for the most use cases, you really want to make sure that your parallelization levels are high. Another limit to parallelization is on the S3 side, and that can happen when you send many, many requests from a cluster. So let's say you have a Spark cluster with hundreds or thousands of machines that all access data. Then what can happen is that you see throttling. So these manifest as 503 return codes, and then you basically, S3 is slowing you down. So let's look at this a bit and understand when does that happen and how we can avoid it. So to understand how throttling occurs, let's go back to this request path that we looked at before. When we send many parallel requests, we parallelize across the S3 front end, and that scales perfectly parallel. So there's no bottleneck there. But if all your keys share a common prefix, then what can happen is that you get a hotspot in this index. So index is basically an alphabetically sorted list of all the keys, and it has partitions that give you a certain throughput or a certain TPS. Now, if all your keys are on one of those partitions, then all these parallel requests you send can land on this one partition, and it can basically overwhelm that partition. And what then happens is that S3 has to basically protect itself and other customers, and so you get these throttles, these 503s. But there's some easy ways we can avoid this throttling, and that is by partitioning our data well. So these prefixes that we'll talk about a bit more in a minute, they give you actually out of the box very high request rates. So you can send up to 3,500 puts per second and 5,500 gets per second. And that means for large majority of workloads and customers, that is enough so you don't run into this throttling problem. But if you have very large request rates from a cluster, then this throttling can occur. And let's maybe question, so what happens when we breach that limit, right? So we have a workload that sends more than this request rate. What happens? Does it mean we cannot get to higher request rates? So your bucket can scale to as much TPS as you need, but we have to talk a little bit about how that works and how you can achieve that. For that, let's talk about this notion of a prefix. So what's a prefix? I mentioned this before, but this notion is a bit nuanced. So a prefix is any string of characters after the bucket name. Let's say we have a bucket called reinvent bucket, and here you see that bucket, and then any part of a key name that comes after that reinvent bucket, after that bucket name, is a prefix. So how are these prefixes now related to request rates, to TPS, and to throttling? Let's look at an example. So let's say we have this reinvent bucket, and on the first day of reinvent, we put some data into a prefix called day one. So that prefix out of the box will give you this 5,500 TPS. And if we send now a higher load than that, we will see this throttling. What happens behind the scenes is that S3 notices that there's a sustained high load on the prefix, and it will issue a so-called split operation. What happens there is that your keys that were initially on one partition are now split into two partitions, and each of these partitions give you these 5,500 TPS. So S3 will basically try to find a prefix that separates your keys into two parts, right? So here in this example, one part of the keys have this prefix day one cats, the other part has day one dogs, and those will land on different partitions. If your load is still higher than that, S3 will do another round of splits. And so in this example, at the end, you will get 22,000 TPS for that bucket, right? And that can go on and on and on until you get basically the TPS that you need. So that sounds really great, right? Basically, S3 scales up to sustain our load, to support our load. So what's the problem? Well, one problem is that you may not make reuse of these partitions in a good way. So let's say on the second day of reInvent, we create a new prefix called day 2. We put our data there, and we start sending a load to that prefix. So here, S3 never saw any load for this day 2 prefix, right? It's new data, it's a new prefix, there wasn't any load previously, right? So it's not scaled up. And what happens again, you will see these throttles until the scaling has happened. So this is really not ideal. What we want to do is we want to reuse these prefixes that are scaled up, right? We did all this work on day 1 to get the scaled up prefix. How can we make use of that and reuse these prefixes? So it's actually quite easy to do that. So here, if we move this day 1 to the right in our key names, then what happens on the first day is that S3 scales the prefix up, right? This common prefix, in this case, it's called data. So it scales the prefix up. You get your 22,000 TPS for that bucket. And what happens on the next day? Well, the day 2 prefix, the day 2 string will be part of that prefix, right? So on the next day, your bucket is already scaled up, your prefix is already scaled up, and you will get out of the box the 22,000 TPS that S3 scaled your prefix up for, right? So the general theme here is that you want to move dates and other things that change over time to the right in your key name, as far to the right as possible. Then any string that could be like IDs or some high cardinality strings, those should go on the left. And that's usually already enough. If you want to have partition your data even better, you can introduce some randomness in your key names. So customers sometimes do that by hashing part of the key and using that as a prefix. So that will give you basically the optimal use case. So this sounds a bit complicated, and there's for some scenarios, it's much easier to actually do that, right? So you don't necessarily have to do this manually. If you use Iceberg tables, then Iceberg actually does that for you, right? So this randomness in the key name is actually one of the things that Iceberg optimizes, and so you will get this out of the box. As Christoph mentioned, we have S3 tables, which give you much higher TPS as well. So for Iceberg tables, use S3 tables because they give you out of the box much higher TPS. And then finally, there's some workloads that are really, really bursty, right? So those really bursty workloads where you don't want to wait for any scaling, for that you can consider using S3 Express because it gives you virtually unlimited request rates. Okay, so this was basically how do we optimize the throughput, right? How do we optimize download by parallelization? Let's now look at a single request and see what can we do there to optimize that single request. So the first thing is request sizes and object sizes, and we'll go into that in a little bit more detail. But one thing you should, if you want to optimize latency, one thing you should be sure, make sure is that you have sufficient resources on the client. So your client should have enough CPU and memory because otherwise there may be some slowdown of the requests. If you really care about single-digit latency, single-digit millisecond latency, you can use S3 Express. So let's look at this request size and how we can optimize that. So all requests, independent of how large they are, typically have the same overhead. So your client has to connect to S3, S3 has to find the data, go to the disk to load the data, and so on, right? So all requests basically have the same, roughly similar time to first byte. But a small request will have only do very little work for that, right? So you have a lot of overhead, and you transfer actually very little data with that request. Whereas a larger request transfers much more data, and so you amortize this overhead, and you get much better overall performance if you use larger request sizes. So here in this example, we have a workload that has small files and small request sizes, and you can see it has a lot of overhead. One way we can manage improve the workload here is to use S3 Express, because it reduces that overhead. But the other way to improve it is to use larger files. So here in this example with the workload, we have a lot of tiny files. Your client has to send many requests, and all these requests don't really do much work. Now, what happens if we bundle files together? So some of these tiny files, we combine them into larger files. Now you can do larger requests that transfer the same data, but it's much more data in one request, right? And you can really reduce the workload runtime here. So let's look at an example of how much this can really improve your workload. So here we used a TPCDS benchmark. So this is a common data lake benchmark for Spark. And we used 3 terabytes of data. In one scenario, the data is in small files, 1 megabyte of size. And then in another scenario, we use the same data, but the file size is larger. It's 128 megabyte. Now, the workload with the larger files runs 8 times faster, and the overall cost is reduced by 25x. That's because you save a bunch of compute cost for running the workload, right? Your cluster runs 8 times shorter. And you also save a lot of request costs because there are fewer requests you have to send. So optimizing file size is really a big lever for improving your workload performance. So now let's look at 2 more factors, and those are prefetching and caching. So prefetching is basically the idea of downloading data before you need it. So we talked about parallelization, and of course we want to parallelize if we can. Sometimes that's not possible, but oftentimes what you can do is prefetching. So here what you do is, in a sequential fashion, what would happen is you issue your request to download data, you process the data, and then you send the next request. Now that's very inefficient, but what you can do instead is you send the request, you get the data, and while you're processing the data, you send the next request to make sure when your processing has finished, the data is already there. So that's really a very common theme in machine learning workloads, where you want to make sure that your GPU has the data when it needs it, right? So you never want the GPU to be idle, and so you download the next batch of data while the GPU is processing the current batch. So a lot of our clients do this for you, but if you run your own application logic and issue requests, make sure you make use of prefetching. So last but not least, caching is really another important way you can improve your performance. The fastest request is the request that you never had to send, right? So basically, oftentimes, your data is separated into a small part that's frequently re-accessed, right? So you maybe query the data from the previous day a lot, but you actually don't query the data that you created like a year ago, right? So there's usually a small subset of your data that's frequently re-accessed and is very, very frequently accessed. And then there's often a large part of the data that's actually not that often accessed. So you can make use of that and cache this data for instance, on your local storage, right? On your local instance storage. You can put that on S3 Express to make use of the better performance of Express. And Mount Point is one way of doing that because it gives you this caching ability out of the box. And another option is to use CloudFront because it will also provide you with a cache for frequently accessed data and speed up requests. Okay, so 3 takeaways for you today. Performance matters, and we'll continue to invest in performance. We've launched a bunch of improvements for your workloads so that they perform better. You want to optimize workload performance, not just single request performance. And so you need to measure that and make use of our new clients and of these performance levers that we talked about. So in particular, you should parallelize, you should optimize your file sizes, partition your data well, prefetch and cache to optimize your workload performance. If you want to learn more, go to the AWS website. Thank you so much for listening, and please complete the survey in the mobile app.